breaking news is that KP is now head of concept engineering at Infinite Technologies in the automotive embedded flash systems. Her talk today is on customizing APIS IQ software for ISO26262 safety analysis, closing the gap from concept to verification. KP has extensive experience in several areas of semiconductor development, including verification, design, and concept or system engineering. In her current role, she leads the activities on the architecture, specification, and safety analysis of the automotive embedded flash systems, working with multiple teams spanning.
So good afternoon, everyone. And thanks, Anne and York, for the excellent talk. And I think the order in which the slides, the talks come is in the right order, because what I would like to cover today is actually to say, okay, we have looked at verification, we have looked at to see how we prove the completeness from a design and verification point of view. But how do we say that what requirements we put at a top level for safety? How do we say that the concepts that we put in, saying I want an ECC here, I want a parity here, I want to put a safety mechanism here, how do we kind of prove that there is a completeness overall? You have the fit rate in the end, which kind of says, okay, this is achieved and we have the particular fit rate. However, from a conceptual point of view, if you have not put in the safety mechanisms in the right places and in the right way, it does not, in the end, you cannot say for sure that you have really achieved the safety goal that you want to see. So this work comes in two parts. So one part of it is what we presented in DAC this year. And that comes to a point where we say, okay, this is how we prove a completeness from a concept level. Then we have extended it for the talk today to cover verification as well, saying how we can use this particular tool in this way that we have used it and extend it to verification to say, okay, one tool, one methodology covers you right from the top level safety goals to your verification. So the tool that we used was APIS IQ. And in theory, this tool is used to analyze systematic fault, or that is the intended usage. But for our safety analysis at a concept level, we use this in order to do analysis of random hardware faults as well. So just like how you say, okay, this is a systematic fault can occur, we also looked at the tool to say, okay, if there was a random hardware fault, what is the effect of the fault on my overall? So this is a slide I just spoke about that, the intended use was for systematic, but we tried to use it for random hardware faults. And in the end, we got some good results. And I had to really go back and say, oh, okay, fine, I need a new safety mechanism here, because actually, you know what, I can't cover the whole path otherwise. So what do we need to start in order to do a safety analysis from a concept point? First, we need of the module, what you want your module to do. Then you need the top level safety requirements of that module. So what are the safety requirements that this module has to meet in the end? So I would like to start actually directly with the flowchart and with the tool usage and how we went about the whole process. So in the beginning, you take the module that you have and you write down the system level requirements of the components of the module. So you start with the very high level requirements saying, okay, these are the functions that my module has to satisfy. And you divide it down into the subcomponents of the module saying, okay, I'm familiar with the hardware. I know that, these are the components that build up this particular hardware. And these are the functions of each of those components of that hardware. So you first create a net where you specify, okay, these are all the functions of this particular module. And then you look at your top level safety requirements and say which of these functions are directly related to that safety requirement. So why this is important is your module can perform, let's say, 6 functions, can behave in 6 different ways. But my top level safety requirement actually tells me that only 2 of those functions are safety relevant. So when I do a safety analysis, there is no need for me to go into details of every single function in the module. I look at the 2 functions that I've analyzed as safety relevant. And then at that point, after you have identified which of them are safety relevant, you can then create a function net using the same tool, which is actually quite a nice feature, because then you can link, if let's say your module has several different subcomponents with several different functions, you can actually link these functions to a top level function and create a function net, which means that I might have a bus decoder, I might have some registers, I might have some other components which have different functions, but ultimately on the top level, they all allow me to read certain registers. I have a decoder, I have a register block. In the end, what is the top level function? It is to read a register. So you can create a net which says, okay, all these functions in these submodules result in a top level function. And this top level function is safety relevant. And I can map down to say, okay, in my module, these submodules have these functions which relate to this safety relevant function. So then it becomes immediately clear to me which are the functions that I need to go more into detail. The next point is where we talk about random hardware faults and systematic faults. So the way we have used it is to say, okay, in general, these are the failure modes of these functions. So we talked about a function net, and then you say, okay, now I take a function within my submodule, and I put down the ways in which this function cannot be met or might not be met. If there was a random hardware fault in my slave interface or in my register, what are the ways in which this module fails? So I have 4 failures. If it is a read path, I say, okay, the data was not received, incorrect data was received too late, too early. So these are different failures. And what is now interesting to me are those failures of those functions which are related to my safety goal. So if you see here, you see 2 of the functions which says facilitate startup, system does not boot, system boots with incorrect system configuration. And this I have used something called as a user-defined attribute of this tool to kind of mark it. It's almost like making a note in my notebook saying, okay, there is a star here because this is safety relevant. So you can use that feature, put a mark there. So next time you come and look at it, you know that, okay, this failure, I need a safety mechanism. I cannot get away without one. The next part is which I found the most useful part of it. Okay, so if I go through the flow chart, we say you select a function and its downstream failure modes in this failure net for analysis. To expand it further, what it means is, like how we created a function net, you can actually add up all these failures together to create a failure net. Which means that if you look at on the right side, on the leftmost side, we have the top level failure, which is the system does not boot, which can be related to the failures in various different functions to say these failures contribute to that top level failure mode. And this is not comprehensive because if you see there are 3 safety mechanisms for one failure mode, there are 3 more for another. Ideally, you would have one strong safety mechanism for one failure mode. But this analysis is at a very high level to, for me to see, okay, do I have safety mechanisms that I have identified for this particular failure? And what happens if I don't? Then I go back through the cycle and say, okay, now I can clearly see what failure I need to address and what kind of failure mode I could put, what kind of safety mechanism I could put for. So what are the results of it? First is a proof of safety. So with a failure mode, I can actually prove that the safety on a conceptual level, it's not a proof in terms of verification, it's not a hard proof in terms of data, but at least on a concept wise, I can say that, yeah, at a first glance, when I look at it, I know that all these failures that can affect my safety goal do have some safety mechanism associated with it. Now, the strength of the safety mechanism, the coverage of the safety mechanism is not featured in at this point. From a concept point, I have safety mechanism that I look. So my first step would be to next see, okay, which are those failures where I don't have any mechanism, and then start working. So here is some evidence of the result where you can see on the bottom slide, the top level safety requirement where a failure violates the safety goal has all these failure modes of the modules, out of which you can doesn't have a safety mechanism. So I need to go back and have a rethink. We put safety mechanisms. And for instance, the safety mechanism doesn't have to be a hardware one. It can be a software one. It doesn't have to be in your module. It can be in external. So you can put, anything over there which says, okay, I have actually something outside this module which will help me to, prevent this failure. Now, the next part is which we added, newly here, which was, I think Mike set us thinking of on how do we relate it to verification? Then we said, okay, actually, what we have done here, if you look at the functions, what are they? They are your requirements. They feed into your verification plan, saying these are the requirements of my module. These are how my module has to work. And these are the things functionally I need to verify to see that the module. Now coming to the next part, I think this is a more interesting part because I feel this tool can also be enhanced to say when at a concept level, I decide, okay, these are the safety mechanisms for these failure modes. The designer should be reviewing what we have done at a concept on a specification level to review and see, oh, these submodules at a concept are actually these hardware modules. These failure modes relate to these gates, to this logic, to this sequential logic, to this FSM. And what failure she's talking about here relates to these flip-flops, for instance. And he or she can put probes at that point to say these are the probes that you can use for your direct fault injection to say, okay, if there is a failure of this kind, this probe should tell you whether the safety mechanism catches it or not. So this particular scheme can be enhanced by the designer to add in probes, which can be used by the verification team for their direct fault injection based on what the concept has specified as a safety mechanism. So you see in one slide how a concept, design, and verification could potentially use a flow and to prove a completeness. So that's pretty much my conclusion that, I firmly suggest that if we had an opportunity that a concept, design, and verification can work on the same flow, the same tool, rather than going with Excels and different kinds of methodologies and so on, there is a lot of benefit to say that the amount of things that can slip through the gaps could be quite minimal. Yeah, thank you.
We have a question in Bristol, so we'll go to that first, and then we'll come back. Paddy, you'll have to come up.
For any tool like this where you're putting in a lot of information, I always have to ask, can you get it out in a usable way for scripting, or making it work with the next tool along? Does it have something like a JSON or XML interface?
Okay, unfortunately, I'm not very familiar with the tool and what the tool can do beyond what I have used it for, but I know that we did try at some point to extract it out into an XML format and into a format that we can directly probably look at for FMEDA and so on, so that we don't have to, do the loop. So I think theoretically, I don't see why it's not possible, but I would maybe, try and contact the tool vendors to see if they can work for it.
Darren Garber from Infineon again. In the beginning, when you were doing the analysis, we were able to very clearly identify things which were safety relevant and things which were not safety relevant. But you can have things which are not safety relevant which could interfere. And how do you handle that in your analysis?
I fully agree with you there, actually. So the freedom from interference story is a very good point. And what I did do, I didn't go into it in detail, was to say which of the failures is a PVSG, which is a potential to violate a safety goal. So you can actually demarcate the failures into PVSG or latent fault or freedom from interference. So that is one of the user attributes that you say, okay, I define 3 user attributes. One is PVSG, one is latent fault, and one is a freedom from interference. And then depending on that, you can say, okay, for the PVSGs, I have these safety mechanisms. For the freedom from interference story, which would anyway come as part of my failure net, I have different safety mechanisms to cover it. Or maybe it's not even a safety mechanism, because if it's a freedom from interference, you could just put a hardware change that makes sure that it does not interfere. You can make it a dual point fault, you can make it a multi-point fault, just make the hardware change. Don't call it a safety mechanism, but then that removes your freedom from interference.
Just one question online. Has this been used before for qualification? ISO26262. Yeah. So can you, and the reports you're generating?
Okay, I believe the tool is qualified because we do use it for ISO26262, maybe not exactly in the way that I spoke about, but we do use it for systematic failure analysis. But more details, again, we would have to get, from the tool.
Okay, no more questions? Oh, sorry, one more question from Bristol.
Raj from Bristol. This is more about the conceptual question. So does the tool give any completeness of the failure mode analysis? How do we quantify and how do the completeness works?
Yeah. So this tool right now, I don't see that it can quantify, or the way we have used it, that you can quantify the completeness. The completeness would be in more of, okay, you have to manually create your failure net, and you have to look and see whether the ones that you have marked as PVSG have a complete failure net or not. So it will be a manual inspection to say that, okay, I can see that I have completely analyzed and all the failure modes that are relevant to safety are covered with safety mechanisms. So I don't see right now a way that you can look at it and say, okay, there is a completeness in terms of numbers. Now, for instance, if you're able to extract the information out into an XML, find the probe points and use it for verification to prove that, okay, these probes are, triggered when this fault occurs and the safety, you prove that coverage. It's not theoretically impossible that this can be extended all the way to your FMEDA, at which point you have your numbers, you have your coverage, and then you have your final proof quantitatively.
Okay, that's all the questions done. Thank you very much, KP. Thank you.